Welcome to ExplaQuiz channel. Today we are learning about RNN and LSTM, two very important ideas in deep learning for sequence data like text, speech, and time series. We'll start from basic neural networks, then move into how RNN remembers context and how LSTM improves that memory. And yes, quizzes will come in between to test your understanding as we go. A neural network is a set of algorithms designed to recognize patterns in data. Just like the brain processes signals, these networks take input, transform it through layers, and produce an output. Real-world data such as images, sound, text, or time series must first be represented numerically. So at the core, neural networks are pattern learning systems made of many connected artificial neurons. In a typical artificial neural network, information flows through layers or tiers. The first layer receives the raw input, and each next layer works on the output from the previous one. This layered processing helps the network learn more complex features step by step. In short, the network gradually transforms input into a useful prediction. A recurrent neural network, or RNN, is different from a normal feed-forward network because it has memory. Instead of treating every input as completely separate, it carries information from earlier steps into later ones. The same operation is repeated at each time step, but the result depends on both the current input and previous hidden state. That makes RNN very useful when the order of data matters. In an RNN, the model takes one input from a sequence, produces a hidden state, and passes that hidden state to the next step. So if it reads x0 first, the resulting h0 helps process x1, and then h1 helps process x2. This is how the model keeps context while training and predicting. Now that we understand how RNN handles sequence information using memory, we can pause and test this foundation. Now that we've covered neural networks and RNN, let's test what we've learned so far.
Here's quiz number 1. See if you can get it right.
Question 1. What makes an RNN different from a standard feed-forward neural network? The correct answer is, it uses internal memory. RNNs carry information from previous steps, which gives them memory. Feed-forward networks do not naturally preserve past context in this way. Question 2. Why are RNNs suitable for tasks like speech recognition or handwriting recognition? The correct answer is, they preserve sequence relationships. Speech and handwriting are sequential in nature, so earlier inputs influence later ones. RNNs are designed to capture that dependency. Question 3. In a layered neural network, what does the final layer mainly do? The correct answer is, produces the system output. The last layer converts processed information into the final prediction or output of the network. Mathematically, the current hidden state in an RNN is computed using the previous hidden state and the current input. Different weights decide how much importance is given to old information and new information. Then an activation function like turn adds non-linearity, so the model can learn complex patterns. The output at each step is generated from this evolving hidden representation. One major advantage of RNN is that it can model sequence data, where each sample may depend on previous ones. That means it is naturally suited for ordered data instead of isolated inputs. In some applications, RNNs are also combined with convolutional layers to capture broader context. So for sequence-aware learning, RNN offers a very important foundation. Basic RNNs also come with serious limitations. During training, gradients can become too small or too large, causing vanishing or exploding gradient problems. Because of this, training can be unstable and the model struggles to remember information from very long sequences. So that covers the core strengths and weaknesses of standard RNNs, and it sets up why LSTM was introduced. Now that we've covered RNN working and limits, let's test what we've learned so far.
Here's quiz number 2. See if you can get it right.
Question 1. What two sources are combined to compute the current hidden state in an RNN? The correct answer is current input and previous hidden state. The hidden state in an RNN is built from present input plus memory from the previous step. That is how context is carried forward. Question 2. Which activation function mentioned in the article helps squash values into a limited range? The correct answer is TAN. The article specifically mentions TAN as the activation function used to squash activations into a bounded range. Question 3. Why do basic RNNs struggle with very long sequences? The correct answer is they suffer from gradient issues. Vanishing and exploding gradients make it hard for standard RNNs to learn long-range dependencies. LSTM stands for long short-term memory, and it is a modified version of RNN. Its main goal is to make remembering past information easier over longer time spans. This directly helps with the vanishing gradient problem that affects standard RNNs. That is why LSTM is widely used for classification, processing, and prediction in sequence and time series tasks. The power of LSTM comes from its gates, which control what should be stored, removed, and shown. There are three main gates: input gate, forget gate, and output gate. Together, they manage the cell state, which acts like long-term memory. This gate-based control is the reason LSTM can handle longer dependencies much better than a simple RNN. The input gate decides which parts of the current input should update the memory. A sigmoid function acts like a filter, allowing values between 0 and 1, while TAN helps scale candidate values by importance. The forget gate then checks the previous hidden state and current input to decide what old information should be kept or discarded. So by this stage, LSTM has already decided what to add and what to remove from memory. Finally, the output gate decides what information from the memory block should become the visible output. It uses the current memory along with gating functions to control what gets passed ahead. Again, sigmoid chooses what to let through, and TAN helps shape the importance of those values. Now that we've covered all three gates, we have a complete picture of how LSTM improves sequence learning. Now that we've covered LSTM gates, let's test what we've learned so far.
Here's quiz number 3. See if you can get it right.
Question 1. What problem in basic RNNs is LSTM mainly designed to reduce? The correct answer is vanishing gradient problem. LSTM was introduced to help networks preserve useful information over longer sequences, reducing the vanishing gradient issue. Question 2. Which LSTM gate decides what old information should be discarded from memory? The correct answer is forget gate. The forget gate examines the previous state and current input, then decides what to keep and what to omit. Question 3. What is the main role of the output gate in an LSTM? The correct answer is choose the visible output from memory. The output gate controls which information from the memory cell becomes the hidden output at that time step. So today you learn the journey from basic neural networks to RNNs and then to LSTMs, along with their strengths, weaknesses, and gate-based memory control. Hope you also enjoyed checking your understanding through the quizzes. If this helped you, like, share, and subscribe to ExplaQuiz channel for more interactive learning videos.